Good morning, everyone. I hope everybody's doing okay today. Our weekends obviously are clearly busy and we got a little bit cooler weather. And so today, a little bit more temperate climate. And then as guess we head into the week, maybe a few warmer days, maybe cooler days. So we're still enjoying the nice weather. Um, we will continue today to complete the discussion on series where we focus more on just the General Taylor series as opposed to the geometric construction that we did last class. That is, when I say geometric construction, I'm saying we're using the geometric series and manipulating that to create really nice series. And what we know is that regardless of the method to create the convergent power series, the series that we actually create is the actual Taylor series. So we don't have to redo anything. We have techniques that assist us in forming a useful power series, and then we keep tabs of them. And so today we're going to see how we can take some of the ideas we've already created to form a list of convenient power series that we can continue to manipulate to produce new power series, and also just some of the techniques that we have at our disposal. That is, the algebra is always very convenient. And then, of course, I need to say something about the binomial series. The binomial theorem you covered in pre-calculus, and that's the case of the finite series, which clearly converges. But in the cases where it doesn't, we need to basically look into that. And the binomial series is a more of a computational type construction. And I think you'll find it interesting to basically fill in the gaps left by the work that we did in pre-calc. On Wednesday, I will probably, well, at this point, I'll know I'll have to do this. I will be recording a lecture and letting you know when that will be available. I have a jury duty summons that I have to fulfill my civic duty, so to speak, on Wednesday. And normally that might mean that if Professor Ron gets picked to serve on a jury, it'll be a short summons where it's quick, and or maybe I'll just get dismissed. I don't know. You can't really protest and say, oh, well, I've got to teach, I need to get a waiver or whatever. Everybody has to go and serve. And so I'll let you know more about that. My colleague, Professor Newman, a couple of weeks ago had jury duty. And so we know that's part of what it means to live in this great country. And so I'm more than happy to do it. But what I'll do is, like I say, once I get the lecture recorded, I will definitely make that available to you in the lecture recording. So on Wednesday, we won't have a live lecture, and that'll maybe give you some time to sleep a little bit later. But I apologize for that because this can't be helped. And again, I think you'd rather have me teaching than being arrested because I don't do my civic duty. I've been very fortunate since I've lived in Harris County. I have not had a jury summons for many years. And so this is the first time that I was chosen. So it is a random process. And those that are selected report because there are cases that have to be tried. And then, of course, you've got a big pool of people that they will then do further selection. And so I'll be part of that process. So um, just remember on Wednesday, I'll send a Blackboard message out to remind you about this so that you have all of your information. And of course, next week, we will have our fourth test. Um, we always need a fourth test before the final exam. And again, the way we've set it up, we don't have such a huge amount of material. My pre-calculus students will have the same, just again, to get you tested before you have the final exam and not have everything bunched up together. And of course, I'll have more information about that. So let me go ahead and share my screen. Lots of announcements this morning. Okay, so when it comes to the Taylor series, what I've written here is Maclaurin series C equals 0. That's really what we spend quite a bit of time with Maclaurin series. They are very, very convenient. And so this is where we think most of our ideas will be pinpointed, so to speak. But like I said before, I need to write down the result that I keep repeating over and over. And this is the major theorem that ties everything together. And I like to use the layperson's terms, that is a convergent power series is its Taylor series. A convergent power series, I'll write out power series this time, is its Taylor series. Now, the thing that we know, and why do we know this? We know what the Taylor polynomial is, and we've just extended it to infinitely many terms. That is, we would say, just like we did last week, all of the power series that we constructed were Taylor series, even though we did not actually compute the coefficients. We get them for free. So the Taylor series is just the extended Taylor polynomial. N equals 0, and then we take the derivatives. Again, remember the superscript n is the order of derivative evaluated at c divided by n factorial x minus c raised to the nth power for some, again, this is based on the ratio test, for some symmetric interval about c. And of course, if it's the entire real line, even better, such that, and this is the part that we have to have, and of course, it sometimes gives us a very nice way to verify that a particular series converges to the function that we think. That is the remainder term. We have the limit as n passes to infinity. And remember, the remainder term looks like this. We take the n plus first derivative evaluated at z. Again, z between x and c for fixed x. Remember, when we've done our problems, you will be given an x, and you know the z exists between c and x. And usually what we try to do is get some kind of upper bound on this derivative. Sometimes it's pretty simple to do, but that's really the way that this particular procedure works. And if that particular procedure gets to be a little bit difficult or maybe not something that we can do, then we look for other methods. But for right now, it's fine, and we will use it. Now remember, everything gets bumped up by 1, and then of course we have x minus c to the n plus 1. So it's just basically taking this, replacing n with n plus 1, but then of course the c is replaced with the z. And of course, if this were going to be true, that is, we could write this as an infinite series, this remainder would need to be 0. That is, this comes as no surprise that the remainder or the extra stuff must converge to 0, because in the limit, this function will equal the infinite series. So we can't have a lot of extra stuff just hanging out that's not converging to 0. So the idea is that when we set up the Taylor polynomial, we would say, okay, what's an upper bound on the error, in the sense of how good is this approximation? And we would look at it that way, or the error would be given and we would work backwards to find how many polynomial terms we needed. That is, what was the degree of the polynomial to achieve that particular error. So the construct is actually really, really useful and then again opens the door to how the calculator works, how we basically use the polynomial to represent the function and then use arithmetic to compute values of the function. Because you can see that when it comes to most of the functions that we deal with regularly, like the exponential functions, the logarithmic functions, the trigonometric functions, the so-called elementary functions, there, you don't just have an X hanging out and you just kind of plug it in and boom, you get an answer. These are more abstract. And when you think about the trig functions, they are certainly abstract when we actually define them as coordinates on the unit circle, which again was the first time you see it very abstract. So the idea in this particular case is this is kind of the key. And this will be the usual method to show that the actual power series converges to f of x. So let's face it, when you start writing down Taylor coefficients, you keep your fingers crossed thinking, well, I hope it converges. You have to have some way of knowing that this is true. And then you can verifiably say, okay, here is a substitute. Here's a polynomial substitute for the function. And so the nice part about the power series, and this is what I was alluding to last class, we have the algebra. So we can actually truncate the series and treat them just like polynomials and multiply them, divide, add, do subtract, things like that we're used to doing. And so all of that algebra, all of those manipulations are available to us, which again make the power series something that we really do want to utilize. And again, as a future engineer or scientist or mathematician or whatever the case may be, the polynomial approximation is central to mathematics. So what I want to do first is just to take a function that maybe isn't very user friendly. And then we're going to go back and talk about how we can use this. But I want to give you some algebra right now. So say, for instance, we're just interested in an example where we compute, in this particular problem, it says compute the first 3 non-zero terms. Compute the first 3 non-zero terms of the, and I'm just going to go ahead and call it Maclaurin series. We'll spend most of our time with that. You can call it Taylor series and then say C equals 0, but then that's of course the Maclaurin. Again, just remember, if the expansion point C is 0, we call the Taylor series the Maclaurin series. It doesn't matter. You can call them all Taylor series. They still are that, but this is kind of a special name. And then of course, the list of power series that we have turn out to be these types where C is equal to 0. And in this case, we want the following function. We've already established Taylor polynomials for lots of functions, and we will use that to create a nice list, and I'll share that with you. Let's just look at secant x, and we're going to do 2 methods with this. Now, of course, secants like tangent, the calculus is not very user-friendly. Sines and cosines are just a dream when it comes to computation, just like e to the x, but this is not the most friendly when it comes to computing derivatives. So what we want to do, again, is compute enough derivatives so that we can actually get a non-zero coefficient. So recall, we will compute, once we're done, we'll compute these coefficients. The nth power of f, or the nth derivative of f, evaluated at 0, again, c is 0, divided by n factorial. So these are the so-called Taylor coefficients. And we've done this before with the polynomials. So you never have to worry that you don't know what to do. If a method just escapes your brain, then you can always use this. The coefficients will always be true. So what I want to do first is just go ahead and compute some derivatives. And then the second method will be maybe a polynomial long division approach. So first we'll have the 0 derivative, that is no derivative, will just be the function secant x. Now, when we think about this, what we're going to do is just compute enough derivatives to get 3 that will be non-zero. And we'll be able to look at the actual derivative formulas and ascertain that. So let me move the mouse over a little bit. So the first derivative, again, now it's like we're in, this would make a great exercise in Calculus 1, perfect exercise. So now the derivative of the secant function is secant x tangent x. Remember when you learned that in Cal 1, you thought, wow, I'm rising up in the standing of mathematics. So again, the derivative of secant is secant tangent. Now, of course, when you think about that, if we evaluated that at 0, that would be 0. So this one's really not going to help us out too much. So we're going to have to keep going. So the second derivative, we'll just use a 2 there. We'll use the product rule. So just go ahead and put the little dot here. So we'll use product rule. We'll be using product rule and chain rule. So these are things you know how to do, but this is always good review. So the derivative of the secant is secant tangent. So we say secant tangent times tangent. And now we take the derivative of the tangent and leave the secant alone. So we have secant x, and the derivative of tangent is the secant squared. Again, very interesting derivatives. Okay, so now this gives us secant times the square of the tangent. And this gives us 3 copies of the secant in the power sense. So when we look at this, we have secant tangent squared, and we have secant cubed. Now as we go through these, you know, we'll look at these. This is going to be a 0, but clearly here that'll be 0, but that's going to give us non-zero because secant of 0 is 1, right, from the unit circle. So here's one that's going to be very helpful. And then of course this one's going to be helpful too. So the idea at this point is that it looks like we're just going to have to look towards the the even order derivatives if we're going to get this to work to get 3 non-zero terms. So let's go ahead and look at the third derivative. Again, this is not a surprise. You're not surprised by any of this. So now we'll use the product rule, put the little dot there. So the derivative of secant is secant tangent times tangent squared, what's left already, leave that alone. And now we're going to leave the secant alone. And then use the chain rule on the tangent. So that will be 2 tangent to the first power times the derivative of tangent, which is secant cubed. So again, the derivative of secant, secant tangent, tangent squared. Then we have secant, chain rule, 2 tangent. That is 2 tangent to the first power, subtract 1, the derivative of, and I've got too many. I'm doing the work in my head, and I don't need to do that. If we see here, we've got the secant, so the derivative of tangent is the secant squared. So I'm not going to go ahead and multiply that and write it. Better to do it correctly. So now we've got these 2 terms, so we check that off. Now let's go ahead and apply the chain rule here. This will be 3 secant squared. And then, of course, the derivative of the inner function will be secant tangent. So let's go ahead and clean this up. We have secant x tangent cubed plus, now we have 2, a coefficient of 2. We have 3 copies of the secant times the tangent. And when I say copies, in this case, powers, obviously, plus, and now we have 3 secant cubed x tangent x. So again, secant tangent cubed. And then notice we've got 2 copies of this. We've got secant cubed tangent, secant cubed tangent. We can do one more level of reduction to add these. That certainly makes our life a little bit easier. So we get 5 of them. 2 plus 3 is 5. So we can look at this, but then kind of, like, well, sad news, right? Because that's going to be 0. But that's the third derivative. That's okay. We expected this. Again, no big deal, but it's the main thing here is what I'm trying to point out here is that no matter how we decide to do this, the derivatives are going to be more complicated, and we've got to pay more attention to it. Just like doing a volume of a solid of revolution, paying attention to the arithmetic and the algebra. So let's go ahead and look at the fourth derivative, which we think is going to save us from all of these zeros. So now if we look at this, again, apply the product rule. So this will be secant tangent times tangent cubed. Again, the derivative of the secant tangent. Now we're going to use, again, the product rule. So this will be secant times chain rule 3 tangent squared, subtract 1, and then the derivative of the tangent will be secant squared. Keep going. Now again, we're going to apply the chain rule. So we're going to have 3 times the 5. That will be a 15 secant squared x times the derivative of secant x tangent x times the tangent that was already there. And then lastly, we just differentiate the tangent. So we have 5 secant cubed. The derivative of tangent is secant squared. So at least in this particular case, we're going to get at least one term that's non-zero, which again, we expected. So let's go ahead and clean this up. So we have, again, secant x tangent to the 4th plus 3. And here we've got 3 copies of the secant power-wise, tangent squared. And here we have 15, so we got 3 and 2, just like we have there. So 15 secant cubed x, not difficult, just easy bookkeeping, nice calculus 1 problem, plus 5 secant to the 5th. So I think it's important that we actually see how we do this. And so now we can, of course, combine these 2 terms. So we have secant x tangent to the 4th x plus 18 secant cubed x tangent squared x plus 5 secant to the 5th x. This weekend I was doing some work with my Wacom tablet, and I like using the Wacom tablet, but the document cam is clearly superior. Being able to write and do what I need to do, like I'm working on a whiteboard, this is clearly easier and was worth the investment. But I like the tablet just because it's fun to use. It's like a toy, but whatever, everything has its place. So when we look at this, we've got all these derivatives. So I'll go ahead, no need to discriminate against the f prime. So we'll just kind of stick that right there. So what I want to do at this point, ladies and gentlemen, is just go ahead and evaluate the derivatives. So let's go ahead and do that. So we're going to say f of 0 is secant of 0. So we can just look here, secant of 0. This is 1. And now for the ones that clearly, just kind of right to the side, I mean, this is what you learned in pre-cal. Tangent of 0 is 0. So we don't have to write down over and over that fact. So now we know that the first derivative at 0 is clearly 0. So just use this over and over. That's 0. And then the second derivative, let's go up to the second derivative. Of course, this will be 0. So I'm just going to go ahead and write that out. We'll get a 0 term plus a 1 cubed, which is 1. The third derivative, oh, and of course, these are all evaluated at 0. So the third derivative, of course, we'll get a 0 there because of the tangent term. And then, of course, we get a 0 here. So that's a 5 times a 0. Again, you could just write it as 0. No need to have really any detail. It's quite obvious. And then the fourth derivative, again, these terms are 0, but then, of course, we get a 5 times a 1. So we just get a 0 plus a 0 plus a 5 times a 1, which is 5. So like I said before, we get this non-zero term here, the second derivative non-zero, and then the fourth derivative non-zero. So this gives us the first 3 non-zero. And when I'm saying non-zero at this point, these are just non-zero derivatives, which clearly will give rise to the non-zero terms. So now we need to divide by n factorial. So this implies that we will have secant of x. Now, and I'll just do a ... for now. This will equal, okay, so now we've got the very first term, f of 0. So that's a 1, not a surprise. And then we skip this one. So we go to the second derivative here. Again, we've got a 1. So we have plus a 1 divided by the 2 factorial, x squared. Then, well, of course, now we get a 0 term, leave that out. So you could write 0x cubed if you like. And then plus the fourth term, we have 5. And then, of course, the n factorial, 4 factorial, x to the 4th. So this is not too painful. It's doable. So we get 1 plus 1/2 x squared. And then, of course, 4 factorial is 24. So we get plus 5 over 24 x to the 4th. And, of course, ... Now, we think about this and we think about the fact that if we're going to do a Maclaurin series and C is the expansion point, that's going to basically confine us to the negative pi over 2 interval. Okay, we can't just mow over infinite discontinuities. Unlike the cosine function, which is defined for all real numbers, we do have the vertical asymptotes upon reciprocation. So now we look at this and we say, okay, well, for this particular branch of the secant function, it is a positive function. So we expect this. We expect this. We're not going to get negative contributions here. So when you're working on these types of problems, you can't just forsake what you already know about the functions. This must represent exactly what the function is doing, at least in this neighborhood. So the key here is that as we work the calculus, we see how the calculus synthesizes with what we already knew, especially in pre-cal when you had none of this machinery available to you. So what we see here is an instance of utilizing Taylor's theorem directly. Okay, so what I want to do now, and I thought this would make perfect sense, is to show how we can use polynomial algebra to actually get this result using something we already know. Now, like I said before, here's the list that I printed out from your ebook. And then, of course, here's the binomial series that we'll talk about. But we've already derived all of these. 1 over x, this is just the binomial, which we know that construction. Log, e, sine, and cosine. And we're going to verify that for one of these, we'll pick one that the remainder term goes to 0. We've already done arctan. And of course, you can do arcsine using the same geometric series approach using the integration term by term. So what we'll have left to do is to talk about the binomial series here. So this is like a mini integral table. And then of course it lists the intervals of convergence. So the idea here is that we know the relationship. So let me move this away. But again, you can go right to your ebook. And what I did, ladies and gentlemen, is I printed this in the landscape setting if you want to have an easy reference. That way everything gets included. You don't want to chop this off. So lots of times as you use the ebook, you may have to vary how you print things, but again, very, very nice. And what could be better to have a book that you can access, you know, on the computer and print pages you need and all. I mean, I was certainly raised with lugging around textbooks. That was a badge of honor at the University of North Carolina. The more books you were carrying around, that was like, oh, you're a scholar, you know. But it's what we had to do. And then of course we had our book bags, and of course as the semesters would transpire and all, they'd wear out and fall apart, and you'd go buy a new one. And of course when you got a new backpack, it was all the rage. Oh, look at my new backpack, I got the best backpack in the world, you know. But the idea is that you use this ebook to your advantage. I really like it. Every time I prepare a lecture, I go straight to the ebook and look at the topics and look for example problems and things. And then of course, I put my signature on it, of course, but it's just a wonderful source of knowledge. I do believe that you learn mathematics with a good text as a foundation. It's important to have that. I can't see learning calculus from worksheets. You need a good solid text. And the Larson text is good. Just remember, ladies and gentlemen, no text is going to appeal to you on every level. That's impossible. But this particular text is good. And let me tell you, Dr. Larson is happy that his textbook is popular. He's a fine individual, and it's good to know that his calculus text has been a success. Now, the second method, let me just call this method 2. Method 2. This would just be, and again, let me come back here again and use the series for cosine. We know what the Taylor polynomial for the cosine is, and we just extend it to the infinite sum right here. We've done this. Or I've made note of it, and it was an easy computation. So for instance, here, we can say cosine of x with c equals 0, the Maclaurin looks like this. And let's just write out several terms. 1 minus x squared 2 factorial plus x to the 4th 4 factorial minus x to the 6th 6 factorial, etc. So the idea here is that we can use polynomial long division, and then we observe secant x is just the reciprocal So now we can look at this and write out a couple of terms. So 1 divided by, and we'll just say in this case, we'll have 1 minus x squared over 2. I'll go ahead and write these out. Plus x to the 4th over 24 minus x to the 6th over 720. So when you look at something like this reminds you of your college algebra days, even though you usually had more in the numerator than just a constant polynomial. But what this is basically saying is that the algebra of the power series is true, okay? So just like using the geometric series to construct a power series, this is an alternate approach. It's like, okay, we constructed the Taylor coefficients. Well, so what if we wanted to use the relationship between cosine and secant and use the power series algebra to determine the same thing? What's so magnificent about the power series is that as long as you're using legitimate mathematics, the result will be the same. A convergent power series is its Taylor series. If you have learned anything in this class, and I do assume you have, this is one of the linchpins. A convergent power series is its Taylor series. That's just like saying functions possessing the same derivative differ by a constant. If you know anything about calculus, you know that. You don't memorize that. You learn the mean value theorem, and then you define what it means to take an antiderivative or an indefinite integral. So the thing is, at this point, ladies and gentlemen, I am hoping that things are starting to come together for you, that you're actually becoming a true math student, that you're raising your level of understanding above the mundane of rote memorization. Until you ascend to that level, your ability in math will always be stymied. It's fine to go out on a limb and make a million mistakes, because that's really the only way you're going to get to the point that you have built up some confidence. Those of you that play sports, or you have jobs, you work for companies, or you do music or whatever, you learn when you mess up. And then that experience forms how you do things when you look into new areas. So this is basically what we're doing here. We're thinking, why not use what we learned in college algebra? It was easy then, and it's easy now. So now let's just go ahead and write this with the long division. So let's just say long division, polynomial. So let's write it down. So we'll just do, I don't know, I've written out 4 of the terms here. So let's do that. Maybe we'll add an extra term. I don't know. We'll see how much we can stand. So we have 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720. So we truncate this and say, okay, this will work. And we divide 1 by that. What's so nice about this is that this is really quite simple. And now let me just bring this down a little bit so our quotient won't be so in the way. So here's kind of the line. We'll just kind of separate all of this. All right. So now we're just going to say 1 divides 1. Well, that's really easy. 1 time. And then we multiply just like regular long division. 1 times 1, 1 times negative x squared over 2. And then we have 1 times x to the 4th. So we're going to do some fractional arithmetic. You're what you live to do, right? And then minus x to the 6th over 720. And we subtract. And you're thinking this is easier than computing all those blasted derivatives, which again, lots of bookkeeping. This is simple. Okay, when we subtract, of course, this absorbs and we get an x squared over 2, and then minus x to the 4th over 24, and then minus minus, plus x to the 6th over 720. So what you see here is something that's very simple in the sense that if you were in college algebra, you could do this problem. You may not understand what you're doing, but you could do it. Okay, well, let's try it again. 1 into x squared over 2, that goes plus x squared over 2 times. Looks very familiar, doesn't it? Okay, we're done. Now multiply through x squared over 2, and then x squared over 2 times a negative x squared over 2, that's negative x to the 4th over 4. And then x squared over 2, in this case, we're going to have, and what's interesting about this as we look at it, and I'm not going to worry about that term, they're getting too large anyway. So we've got x squared, x to the 4th, so that's going to be an x to the 6th. And then we have a 2 times a 24, 48. So I'm not going to worry about that term. That's larger than we're going to need. So we'll stop there. Again, just go ahead. We only need to get 3 non-zero terms. Maybe we'll get a 4th, but no need to go that far. You can, but we're not going to do it. So now when we subtract 0, and then at this point, we can just look for common denominators. So do a little sidebar. Negative x to the 4th over 24. And again, this is minus minus. So this will be plus x to the 4th over 4. Now what we want to do is get a common denominator, and notice this is just what? 4 factorial equals 2 times 3 times a 4. So now with a common denominator, so we're just going to need a 6 right here. So we're going to get 24 negative x to the 4th plus 6x to the 4th will give us 5x to the 4th over 24. Now, of course, you don't have to do all of these. You can just look at the actual fractions, but just use the factorials. So here we have 5x to the 4th over 24. That looks pretty familiar, does it not? That's the last term that we computed in our previous method. This is easier if you just do the algebra, just do the arithmetic. And then, of course, here, let's just go ahead and generate this term. Notice the 720, we can do this the same way because we're going to be lazy. 6 factorial is just 2 times 3 times 4 times 5 times 6. Okay, well, that's a 48, right? So here is the 48. That's the 2 times a 4, which is an 8. 8 times 6 is 48. Just go good old general math. I call that number theory now in pre-cal because it's that important. And so, of course, here, this gives us a 15. So now we get a common denominator. Let's just go ahead and look at it. We're going to subtract. So let's write this out. X to the 6th over 720 minus x to the 6th over 48. So we'll get a common denominator of 720. So we get x to the 6th. And then, of course, here we have to multiply by 15. So minus 15 x to the 6th. And that will give us a negative 14 x to the 6th over 720. So that goes here. Okay, so all of this just requires a little bit of extra arithmetic, and you don't have to write so much detail here. What I'm trying to show you is how you can use the factorials to make it easy. So now when we divide 1 into 5x to the 4th over 24 gives us our last non-zero term that we were tasked to do. Okay, so if you multiply now, you get 5x to the 4th over 24. And now, again, we're not going to worry about these two. We got more than enough to do. So this will be a what? A negative 5x to the 6th. And then we got a 24 times 2, which is a 48. Now, if you want, when you subtract, you're thinking, oh, Professor Ron, can we just generate one more term just to see how this works? Well, here it is right here, ladies and gentlemen. So let's just go ahead and do the same song and dance we did before. So we'll have negative 14x to the 6 over 720. And of course here minus minus, so this will be plus 5x to the 6th over 48. Now, of course, again, we need the 15 here. When we compare, we've got to have the 15. So this will give us a 720. So we have a negative 14x to the 6 plus, and now, of course, the 15 times the 5 will just be what? That gives us a 75. So 75x to the 6. So this will be what, a 61. 4 from 5 is 1, and then that gives us a 6x to the 6, 720. So we get 61x to the 6, 720. Now I will say this, ladies and gentlemen. Now there's the extra term right there. So we can go ahead and just stop with this. So we'll have plus 61x to the 6 over 720. Now I will say this is a whole lot easier than computing derivatives. And if you were seeing how complicated it was just to get easy lower level derivatives, can you imagine doing the 5th order and the 6th order to get that? So the key here is that this is easy if you just suffer the basic fractional arithmetic. But that's what makes the analysis so nice, is that you're not forced to use any one method. So now you can think, well, I could probably Google this and find even more elaborate tables of power series. And of course you can. That's what's nice about all of this. You can always get further information, but now you can see we have the same result. That is secant x. This problem kind of covers so many different details of manipulating power series. You know, you can manipulate them algebraically. You can make substitutions, replace x with some other function to get a completely new series. The idea is that if you can see this, then I think you'll actually believe it. And then of course, division is not sacred. You could multiply. You could just do the distributive law and multiply two functions to generate non-zero terms of a new series. Again, using series from the list. You don't have to start from scratch. And who wants to do that? I mean, you think about it. You think about it, if you need e to the x times sine x, use the sheet. Multiply a few terms, use the distributive law. I mean, otherwise, what do you think you're going to compute those derivatives with the product rule and go crazy? See, the thing is that the luxury of the algebra of the power series makes all of this legitimate mathematically. So now we can just reiterate what we have: 1 plus x squared over 2. And of course, I write a lot of these in my lecture notes too. So you get additional help if you want to look at those. So etc. So I just added an extra term there because it was fairly simple to do. So this is the method 2. And even though it seems maybe still work, it's less work than computing all these derivatives, because when you think about this, I mean, just harder than what we did with polynomial long division. Certainly doable, but more challenging. But you always get to choose that. So now again, think about what you did in pre-cal and think how this basically is consistent with those results. So I think the way of actually taking a geometric approach to trigonometry the first time around with the unit circle and the right triangles is genius. It's genius, because how is an infinite series going to help you solve a problem about a right triangle? How is an infinite series going to help you graph the sine function? Okay, now as far as even and odd, that would be a walk in the park. But you see that there are different uses for different interpretations. That's what math is all about. You take what you already know and you interpret it differently in a more abstract way and push the knowledge even higher. So if some of you decide to go to graduate school, you're going to think, well, I'm still doing the same thing I did at San Jac or in high school. And it's true. You're just moving the discussion to a higher level, a more abstract plane. And it's the abstraction, ladies and gentlemen, that allows us to create new math. We have to live in the abstract world to be able to solve problems in the real world. And that is something you either accept or you don't, or you always dislike math. If you don't accept the abstraction of algebra, then you never can do algebra. And that's unfortunate because a lot of individuals who say they don't like math, they just don't accept the idea of it. And once you do, you can do anything you like. Now, what I wanted to do is show you how the Taylor's theorem basically says this works. Okay. With the geometric construction, we get the series. We start with the function and we write the series, we're good to go. And we even validated that with one of the ones that we constructed with a value in the particular interval of convergence last lecture. So now what we want to do is say, let's take a series from our chart, and I'm going to take the e to the x and show that it actually is, e to the x is exactly this, using the analysis of the remainder. So we want to prove, in this case, that e to the x is actually this series. Now I'm going to write it out, then I'm going to put out some terms. So of course, when you do your Taylor polynomial with the Maclaurin, that is that C equals 0, you get something like this. So you get 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, etc. So, and this, ladies and gentlemen, is true for all x. Just like we have for sine and cosine. We're like, wow, we like this. This is amazing. And what's amazing about this is that, again, as you do your engineering problems, as you do your physics problems and all, your physics professor really does enjoy taking a few of these terms as a replacement for e to the x. And the idea is when your calculator is functioning, these are the polynomials that are being evaluated. Okay, so the nice thing about calculus 2 is that things actually start to come together, and you see that it is all based upon arithmetic. So now what we want to notice is, if we're going to prove this by Taylor's theorem, then we just need to check out what the derivatives are. In this case, these are very attainable, kind of like what we did with the Taylor polynomials. So we observed that the n plus first derivative, in this case, well, just in, if we have to look at the remainder, is e to the x. This is, again, for any order of derivatives. So we need this when we actually compute any kind of bound or any kind of analysis about the remainder term. Now what we want to do is fix. So you're like, yay, that's so nice. So we say fix a real number. And we're going to actually use a special limit. And I'm going to show you why this special limit is true, since I didn't do it at the time. So fix x element of R. Then there exists, this is Taylor's theorem now, z between 0 and x. Again, such that, so let's write it down. We fixed an x, but we still call it x. It's not like some of the problems, x was 3/10 or something. We fix this x, and the remainder is the n plus first derivative evaluated at the z that lives between 0 and x. And then, of course, we have n plus 1 factorial, and then, of course, x minus c, which is x minus 0, or just x, to the n plus 1. This is the remainder. That's part of Taylor's theorem. And then the extension to the infinite series requires that this actually converge to 0 as n passes to infinity. Then the limit, so let's just go ahead and use our little properties of limits, and by looking at the absolute value. If we can show that the limit of the absolute value is 0, then we get that for the function. We use that in section 1 of chapter 9 when we didn't know anything. So n approaches infinity, the remainder so now, of course, all the derivatives look like this, e to the x. So we have e to the z. Of course, e to the z is fixed too because it lives between 0 and x from Rawls' theorem. And then we have n plus 1 factorial. And then we have x to the n plus 1. So we can go ahead and factor the e to the z limit as n passes to infinity. And now, of course, if you like, just leave this all inside if you want. And it, just like using the continuity that we've used before, just to make the process easier, move the limiting process inside. So we have e to the z limit as n passes to infinity of x to the n plus 1. Very, very simple algebra. And then, of course, this is the special limit where I think I wrote it as a fixed k to the n divided by n factorial. Here we've just replaced n with n plus 1. So this is a special limit. This limit is 0. This is a special limit that is in that list that I gave you. And I told you we'd eventually use it. So this will be e to the z times 0, which is 0. So if and only if the limit as n passes to infinity of the remainder term is indeed 0. And that's what we have to show. So when we work with Taylor's theorem, if we want to be assured that, I mean, you know, we looked at power series in 9.8, basically saying, okay, you know, find the interval of convergence and all that, but we weren't constructing series there. We were just learning how to deal with power series, okay? But now the power series have taken on a new characteristic in the sense that the power series represents the function. And so we can't just assume, you know, we've got these Taylor polynomials and we're like, okay, is this even going to work? Well, we saw in many cases that it did appear to work, that we could actually rein in the remainder, that we had control over it. And so the control that we need to be able to, you know, with certainty say that this equals this is to show this. This is one method of doing it. And the methods do vary depending on the complexity of the function, and namely the remainder term. So when we make this substitution, we do it with mathematical certainty. We can't always be so cavalier to say, okay, well, I just computed the Taylor coefficients, this will work. Well, you mowed over some infinite discontinuities, and of course, your foundation may not be suitable. So the idea here is that we just have to make sure that if we're going to make this replacement, that this does actually converge to that function. And we see that. So now, and I'll just say this, you use the same limit, similar argument. We don't have to do this for the geometric constructions. We got those for free. Similar argument for cosine and sine. So the idea is, if we don't use the alternate approach where we can use the theory of convergence for the geometric series, we've got to rely on this or some other method. Okay. So let me just share with you, and I didn't do this at the time. You're thinking, what's up with that special limit? You know, Professor Ron, it seems like you're purporting that the factorial function wins the game as far as growth, and it does. And so here was the special limit. I thought I might say something about this. I was just scratching this down, and I thought, well, I can figure out a proof, and I think I've got this written up in the lecture notes. So, for instance, here's how I wrote it: fixed k. This is important. For fixed k element of R, we have the limit as n passes to infinity of k to the n divided by n factorial equals 0. So this is what we used as the special limit. So it's important when you're doing these problems with Taylor's theorem that you fix an x, and then what you see is that the x has no bearing on the limit, and then any x could have been chosen. That's why now for this, and I didn't explicitly state it, but the x doesn't matter here. So this is true. This is true for all x element of R. That's why we have this. The arbitrariness of the x that's fixed is again a linchpin of this argument. I mean, when you start to write down an argument, you've got to say, well, what's varying and what's not. Okay. So when you look at this, you're thinking, and here's a very simple way to look at this. First, what we want to do is the following. Why is this true? And it's not difficult at all. Fix m a natural number such that, here's a real simple argument, such that in this case, the absolute value of k, we're going to use the same thing we did before, is actually less than m. Okay, so we fix some natural number that's bigger than the absolute value of k. Say k is, I don't know, 15/2 or something. So m could be what, 20, doesn't matter. And we don't do also the following: fix n a natural number such that n exceeds m. Now, the thing here is you're like thinking, well, okay, so how is this going to help us out? Well, what we want to do is now look at this particular construct with the uppercase n. Then look at the absolute value, k to the n divided by n factorial. So we're thinking, okay, so we're going to fix this n, and then what you're thinking, oh, I see. So this n's just going to march off to infinity if we can get a nice result from this and then have what we need. So here's what we're going to do. We're going to say first, we're going to take the absolute value of the numerator and the denominator. So this will be absolute k to the n. And then, of course, we'll have n factorial. The absolute value of the n factorial, of course, is just n factorial. That's a positive number. And now we can use this inequality. So this is going to be less than or equal to, or if you want to say equal to or just less than, this will be m raised to the n factorial. Okay, so now we can use this. So we have this strict inequality, or you could be less than or equal to, won't make any difference. And now you're thinking, is this what we needed? Absolutely. So what we're going to do is we're going to break it down. We're going to use this relationship here. So the n factorial can be written as, and I've written it here, 1 times 2 ascending to m, because m is strictly less than n. And then we're going to have the piece that starts with m plus 1 and ascends to n. And then, of course, we'll have m raised to the nth power, and then m by the laws of exponents raised to the m minus n power. So the key here is that we've got what? M factors here and m minus m factors here. So what does this give us? Well, this equals, so we have m raised to the nth power divided by what? M factorial. And now, if you will, we can break all of these down. We can just attach all of these to these factors here. We've got n minus m copies, and we've got m minus n factors here. So we're going to just write them as all separate factors with the m and the corresponding denominator. So we'll have m over m plus 1, m over m plus 2, and we'll ascend to m over n. Now, what we notice in this case, and this is the interesting part, and this goes right back to how we were approximating fractions. Notice all these m's are constant, but this is the smallest denominator. So this fraction here is going to be bigger than all of these, okay? So, and they're all less than 1. So now we've got what? Less than m to the nth, which is a constant. This is just a constant right here. That's just a number. And then we have what? M over m plus 1 to the n minus m. Now, this is a constant. They're all constant, but we'll just say element of R. And this, of course, is less than 0. And so this will tend to 0 as n tends to infinity. So the key here is that we can make this as small as you like. We can make it smaller and smaller and smaller. So the idea is that this argument is just based on simple arithmetic and simple uses of numbers in absolute value less than 1. And we know from the geometric series that this particular limit will always be 0. So regardless of where you start with k, you can always make this small. And then, of course, as n gets larger and larger, this is still going to go to 0. So now this implies, if and only if, now we can just go inside to the limit. Absolute value goes to 0. So does the limit without the absolute value, if and only if n, and you think I could probably use the lowercase n there, but it doesn't matter. N works. So now I'll just use the regular n, k to the n. Well, here, let me write that so you can see it. K to the n factorial equals 0. So this is a real simple, very intuitive type argument to show that this particular limit is 0. And so it's important. It's you don't just want to wave your hands over it. So I think now when you look at the Taylor's theorem, if you use this, you can do it with some kind of confidence. Again, for the fixed k, even if n is getting large, the thing is that's growing pretty fast, but the n factorial overtakes it. And that's not a surprise. Lots of work has been done on the mathematical properties of the factorial function. Combinatorics has just blown up in the 20th and 21st century. And so you can spend days, just years studying the factorial function and binomial coefficients. Now, let's look at another series that's very important. It's the binomial. And we just want to look at some construction processes. So it's the same that you did in pre-cal. That is the binomial series. And it's listed here. It's listed here as the last series of the chart. So the binomial series. So we get to use at least a lot of stuff that we used in pre-cal. So we're going to say 1 plus x, this is the form that Newton created, equals, and we'll use binomial coefficients, n equals 0, to infinity. I write up a power series type proof of this in the notes. It's a little bit long-winded and maybe not the most useful at this point, but you can certainly look at it. It just uses a lot of manipulation of series. So when we think about this, we think of Pascal's triangle, and especially when k is a natural number, and we think, okay, well, we just have these coefficients, and we've got the powers of x, and since one of the terms here is a 1, everything multiplied by 1 is just the same thing. So we get this, and then we think, okay, what's the restriction? X will live between -1 and 1, and so you're thinking, if we can ever include the endpoint, we could use this to approximate square roots, maybe the square root of 2, and use other ideas that help us to understand why our calculator works. Now, here's what's important, and this is the more complicated end of this. Endpoint convergence. That is, you're thinking, we often test endpoints when we look at power series, but endpoint convergence depends upon the value of k. Depends upon the value of k. So, for instance, where it makes sense, you're actually going to get the convergence here. And so this is not going to be something you're going to have to test separately. It's a little bit more sensitive than some of the arguments we have used thus far. So what I wanted to do is kind of give you a summary of what happens at the endpoints. So for the absolute value of x equal 1, these are basically endpoints. We have the following. That is, number 1, when k, now here's what's interesting. When k is positive, this implies, so we're thinking, if k is just a positive integer, this is just a finite series like we did in pre-cal. We're not saying that that's unimportant. We know that converges. I mean, not very interesting. So that we get for free, but we already knew that. But when k is positive, we get the series converges absolutely. So we're thinking, wow, that's pretty cool. When k is positive, we get absolute convergence at the endpoints. So we can include the endpoints here, okay? So if we did x plus 1 plus x to the 1/2, boom, that'd be a way we could approximate the square root of 2 with this series, okay? So 2, if k, we'll have examples where this would be true. Say k lives between, or if it's 0, that's not very interesting at all. I mean, we just get 1, so that's not very interesting. But if we're less than 0, but greater than -1, we have series converges conditionally. And then, of course, x not equal to -1. Of course, that would make it infinite. So that would be a non-starter. If the k is less than 1, everything gets pushed into the denominator, and then of course you can't divide by 0. So that would be divergence. So this is still good. It's still good. We're fine with that. And then of course, if k, and this is kind of obvious, is less than or equal to -1, this implies series diverges. So we're not really going to care about 3. I just wanted to go ahead and kind of put your mind at ease that we're going to pretty much focus here. Okay, so there won't be this checking the endpoints with the binomial series. Again, this is a little bit more sensitive than what we've been doing. And if you go on to take some advanced calculus and more real analysis, you'll look at the binomial series even in more detail. So the thing that's interesting here, and I've got some examples I want to talk about, is that we apply the same techniques we applied before, but now we have to look at binomial coefficients that are a little bit weird in the sense that we don't have, if we've got non-integers here, then it's a little bit different. It's still computed the same. So for the binomial coefficient, this guy here, and of course that's flipped around. You're used to seeing the n on top, binomial coefficient. This is just using the notation of our text, which is fine. We have something like this. That is k choose n will just be a falling factorial. That is, when we think about this, we have k times k minus 1, and we descend to k minus n plus 1. That is, we get the n factors here, the k choose n, so to speak, divided by n factorial. n factorial. It's really hard when I teach pre-cal, we have it flipped. So you just have to remember that the notation here is flipped of what you had in pre-cal. So what I wanted to do first is an example. Where is that one that I have for the square root? Yeah, I want to do that one first. Yeah, let's do this one. This will be a nice example since I already alluded to it. You can just work these all day long. They're fun. So I thought the best way to introduce this, you're thinking, well, Professor Ron, I'd do the cheap way. I could just say, n equals 0, I'm always going to get 1. So in general, we would say 1 plus x to the k will just be 1 plus, in this case, and we're thinking that'll be kx plus, if you want, and we can just generate these in the abstract, then we get k minus 1, k times k minus 1 divided by 2 factorial, which just mimics this from our list here. So we'll say k times k minus 1 over 2 factorial, x squared, etc. So you're thinking, okay, that's not so bad. I can just, be kind of cheap here and do separate terms and generate 3 or 4 non-zero terms, be done. And there's absolutely nothing wrong with that. But I want to show you just a couple of techniques that would allow you to consolidate things to get the complete series. Because, of course, when you look at this, you're thinking if you just started differentiating, you would get these kinds of coefficients. So again, this just uses the definition of the binomial coefficient, where again, this would be k choose 0, which by definition just gives you the 1. This is k choose 1, which is just k. And this is just k choose 2, which is again the falling factorial, 2 factors, k times k minus 1 divided by 2 factorial. So this is exactly what's going on here, okay? So you can always allude to that if you're just interested in generating a few terms, but I wanted to go ahead and do the square root. So let's notice a couple of things here. For instance, say we have k equals 1/2. I'm gonna do this a couple of ways. You can enjoy this and have a good time with it. That's really what the binomial series is all about. So we can say 1/2 choose 0. That by definition is 1. Anytime we have the 0 in, you want to make this user-friendly, that by definition is 1. And we've used that before. And then we'll say, so we've got k choose 0. Now let's use 1/2 choose 1. Now it's weird, but again, it's the same thing. It's just now that we've got fractional arithmetic in the factors. So this is just going to be what? Let's follow. This will be 1/2, again, divided by 1 factorial. Now that's kind of beating it to death, but that's just 1/2, right? Okay. And now I saved this for last because it's the most fun. Well, kind of last. Now here, let's do the same thing. Let's see, 1/2 choose 2. Use our definition like we use here. So we've got what? 1/2 and then 1/2 minus 1. That's why this is really important. This is imperative here. This is the only combinatorial stuff we'll have to use, divided by 2 factorial. Well, now, of course, we can clean this up a little bit. This will just be 1/2 times a negative 1/2 divided by 2. Okay? Well, then, of course, that'll just be what? Negative, bring everything downstairs. We got a -1 and we got 3 copies of 2. So that's -1/8. All right? Easy. So 1/2 choose 2 is -1/8. So you can always opt for this approach, ladies and gentlemen, to generate a few terms. Let's go ahead and get 1/2 choose 3. Let's generate 4 terms. So there's no reason to not understand the binomial series. The complexities of dealing with the algebra can be a little bit daunting at first, but it's based on what we've already been doing with our manipulations, no difference. And I'm going to give you a nice little identity that I think will be very interesting for you. So now we'll do the same thing we do here. We'll do 1/2 minus 1, 1/2 minus 2. Remember, just following the dictate here. Remember, for 3, we get 1/2 minus 3 plus 1. So that's 1/2 what? Plus 2. So well, minus 2 in this case. So right there, right there. Again, -3 plus 1, right there. Exactly. Okay. No, this is the generalized formula, and it works for any value of n that you're substituting. Okay. And then, of course, 3 factorial. Well, same song and dance. Let's just write this below. So now notice we're going to get a 1/2, a -1/2. And now notice we're going to get a -3/2 because we're subtracting 2. So we get a -3/2. And then, of course, 3 factorial is a 6, right? So we get 6. Let me write it this way. Let me write it as 2 times 3. Okay, 2 times 3. 1 times 2 times 3. Now, we've got 2 negatives, so that's a positive. So we've got a 3 that remains upstairs. And then we're going to have 1, 2, 3, 4 copies of the 2. And then, of course, times the 3, and that's going to absorb. So if you write your work the way I've been teaching you all term, you don't have to rely on a fancy calculator that you're probably just going to make a million mistakes anyway, trying to punch all the numbers in. Just do it the way I've taught you. So now the 3's absorb, and we just get what? 1/16. And I did a little simple calculation here with these terms. And then we'll do this, in a more general setting to give you an idea of how you can work with the formula here to get a nice infinite series without having to compute all of this. Now you're thinking, Professor Ron, what starts to develop here is a pattern. And if you look at this, you can see this pattern developing, powers of 2, and then you're going to get odd integers in the numerator if you keep moving. So I'm going to show you a way to uncover that in a more general setting. But notice now, we can say, okay, well, we've got what? 1 plus x to the 1/2. We'll say equals. So let's just go ahead and fill everything in. We've got 1. So I'm going to use my coefficients here. So we have 1 plus, let's see. Oh yeah, I did this right here. I wrote this as extra, and now it's becoming center. So we have 1/2 x minus 1/8 x squared plus 1/16 x to the 3rd, etc. Okay, now this is what I was mentioning. If we think about what we have over here, let's see. Oh yeah. For the positive k, we get absolute convergence at the endpoints. All right. And so now if you look at this, you're thinking, okay, this will work for X living here by our convergence result. So now if you like, you can say, okay, well, I'm going to let X equal 1. So I could have square root of 2. So now I could use these first 4 terms to approximate the square root of 2. So I'll say approximately 1 plus 1/2 minus 1/8 plus 1/16. Now, when you look at this, you're thinking, okay, you could use your Google, but let's just go ahead and reduce it. Just get a common denominator of 16. So now this will be a 16 plus an 8 minus a 2 plus a 1. So now, of course, if you like, there's a 17 and then a 6. So a 17 plus a 6 over 16, which is a 23/16. Now, if you actually divide this, you can use long division or use Google. This will be 1.4375. Now, of course, when you're approximating the square root of 2, you can actually use more terms here and get a better approximation. But what you're seeing here is this is exactly what I was saying before. This gives at least a 2 decimal, or actually 1 decimal approximation for square root of 2. So the idea here is that for this particular convergence result, we can get approximations for square roots of 2. We can get approximations for any square root, but this is when we have to start using our arithmetic that supports the convergence results. So this is what I was saying. Calculator works this way. This is what we've been doing from the very beginning. So you're thinking, okay, if I'm doing a problem and I just need to generate a first few terms of the binomial series, I'll just go ahead and compute the binomial coefficients just like here, like Professor Ron did. Why not? Now, of course, in this case, we've got the X and all that. It could be different. We may have to manipulate a little bit because remember, when we use the binomial series, we have to have 1 plus something. That something could be other than X, but it's got to meet this, and then we substitute into here. And we have to figure out the K in this form. So this is important, ladies and gentlemen. You must respect the form of the series. So if we were going to do this problem in a more general setting, let me show you how you could do that. And I'll give you some tricks that will work. I've got another example here that'll be kind of interesting. So in this particular situation, what I did is I just looked at the series that we just computed, the first 4 terms. I want to look at this in a more general setting in terms of the coefficients. So here we can say write the Maclaurin series for f of x equals 1 plus x to the 1/2. Of course, you know, you can have this downstairs and have a k is negative 1/2. You do it the same way. The computations are done exactly as I've shown you. So then you could say, okay, binomial theorem. Binomial theorem. So we'll have 1 plus x, and I'm going to show you what's convention with these types of problems so that you can get a nice, beautiful result. So you're thinking, if you were doing a computer program and you wanted to give a nice, beautiful series for this, let me show you how to do it. So now we're going to say, all right, well, k equals 1. This is all set up for the theorem. So we have n equals 0 to infinity. And then we have 1/2, again, k equals 1/2, and x equals x. The x here, the x is x, okay? So we have n, and we have x to the n. Now, what's customary to be able to use the definition of the binomial coefficient is just to kind of extract the first term, which we know is just going to be 1. So the very first term will just be 1/2, choose 0, x to the 0. That's just the 1 plus n equals 1 to infinity, 1/2 n x to the n. That is usually a convenience to make the manipulation here a little bit easier. Okay, so now, of course, this is just 1 by definition. Now what we want to do is use the definition of the binomial coefficient, and I'm going to show you some algebraic manipulations that will allow us to get a generalized formula. Now, I will say this, when you're just looking for a few terms, do what we did before. Just go ahead and generate each term using the definition, the binomial coefficients, and then boom, you've got it. And those are the same as the Taylor coefficients, or you can say, you know, Professor Ron, I'm going to be completely lazy. I'm just going to use these formulas right here because, you know, I'm not going to sweat too much. Okay. You've got the use of this if you want to do that. All right. Same thing. So now what we can do is say, well, what's the definition here? Okay, let's use the definition of binomial coefficient. So we have 1/2 minus 1, 1/2 minus 2, and we decrease to what? 1/2 minus n plus a 1, just using the definition here, this definition right here, where I've substituted 1/2 for k. It's exactly what I've written here. No difference. Okay. And I know you didn't have me for pre-cal, so you probably didn't use that definition. I don't know. It doesn't matter. I'm telling you what you need now. So now, what else do we have? So n factorial, okay? And then I'm going to give you that funny little identity, x to the n. So now you're thinking, this just looks like what we did before, Professor Ron. You know, we were doing the factorial definitions and for the binomial coefficients, we're seeing all of this. So what I want to do now is just make some obvious algebraic manipulations. Here we have n factors by definition, n factors. So this will be 1 plus n equals 1 to infinity. So let's go ahead and factor all of this, make this look more beautiful, so to speak. So we've got what, 1/2, and then we have a negative 1/2. Then we get the common denominator here. That's going to give us a what, -3 over 2. And then the next term I left out, but I'm just going to write it. It's going to be a -5 over 2, etc. And now we get down to the n, we're just going to get a common denominator of 2. And I'll eventually rewrite it, but I'm going to say, in this case, 1 minus 2n plus a 2. N factorial, x to the n. Now, notice we have this negative here, so we want to do the same thing that we're going to be doing here to write it in a way that it looks very user-friendly, so to speak. So here's our little sidebar. Take this over here, so I don't have to write this down 500 times. So this will be, if you like, factor the negative. First, before we do that, let me just make it simple. Go ahead and add up everything. So this is a -2n plus a 3. And then factor the negative like we factored here. So we have a -2n minus 3. So now when we look at this part here is the negative of 2n minus 3. So it's got the negative out front like all of these do. So now we get 1 plus n equals 1 to infinity. Now notice each one of these has a factor of 2, and there are n copies of it for the n factors. So we get 1 over 2 to the n. And now with the n minus 1 factors, that one doesn't have a negative. The n minus 1 remaining factors all have a negative. So we can say times negative 1 to the n minus 1. You could write n plus 1. It wouldn't matter. It'd be the same parity. And then what's left? Well, let's look at this. We've got a 1. So that's just a 1. So we've got a 1, a 3, 5, 2n minus 3. We don't ascend to 2n minus 1, and we'll remedy that. Divided by n factorial times x to the n. So this is a way you can generate a compact sum without having to write down a lot of terms and then trying to figure out a formula that may or may not be correct. That's one way to do it, but this is actually cleaner. So now we get 1 plus n equals 1 to infinity. So now let's bring everything downstairs. We have the 2n times n factorial. That is, just go ahead and bring this downstairs to join the n factorial. And then we have the negative 1 to the n minus 1. And then we have 1 times 3 times 5 ascend to 2n minus 3. Now, of course, you're thinking this is fine. And put in the x to the n, I will. You're thinking this is fine. That I know the pattern here. No problem. I can do this. I mean, this would work fine. But the thing is that there's a nice identity here, and I'm going to show you how to use it. This is what the WebAssign gives you, and I'm all for it. It's a nice identity for this finite product. And so if we put in the 2n minus 1 and then pay for it here, we can use a nice, beautiful identity. And this will be force x to the n. Now, why did I do that? Well, we can make this even more small. We can put it all together. Here's a nice identity, and you can prove this by induction or just by hitting this. That is, this product, here's a little lemma. 1 times 3 times 5 ascending, again, for n is a positive number, positive integer, to 2n minus 1. This is just a way of killing all the even factors. When you multiply, do like an n factorial. You get, in this case, 2n factorial divided by 2 to the n times n factorial. This is a very interesting little result. You don't see a lot of identities for finite products. And so now you're thinking, for this part here, for this piece right here, we can just replace this with this. And so you can even make this formula look even nicer. So this will give you 1 plus n equals 1 to infinity. So we have our negative 1 to the n minus 1 or n plus 1, it doesn't matter. The thing is that this will start out when n is equal to 1, it'll be positive. And if it's a n plus 1, it's a 2. So you still get the positive 1. So this you have control over. And then, of course, now if you can look at this, we'll have a 2n factorial upstairs right there from the formula. But now downstairs, we get 2 copies of the 2n, 2 to the n times n factorial. So we have 2 to the n factorial, quantity squared. And then, of course, that lone 2n minus 1, because we had to pay for it, times x to the n. So what we end up with, ladies and gentlemen, is a really, really nice formula that's compact. Now, in some cases, some authors will write this, they'll just go ahead and tack on the additional 1/2 x and then start this at 2, but that's your choice. It doesn't matter. I won't write that down. You can also do that too. It just really depends on how the problem is stated for you to write it. This gives you the infinite series in all its glory, so to speak. Now, you're thinking, if you wrote it like this, stopped here, would that be okay? And, compactify a little bit? Yeah, that'd be fine. That's fine. There's nothing wrong with that. But this little identity here will come back to haunt you later in your life. So it's kind of a nifty little thing. You can do an inductive proof for this. So you could write it out and see that it actually works. You can do an inductive proof, like I said before, to prove that. But you could just write this out and show that the even factors absorb. It's really quite remarkable how this works. And so I thought it was neat how your homework just says, well, try this identity to make your series look a little bit more neat. So this is a more beautiful result, whereas there's nothing wrong with writing out a few terms that, like we say, like the sine series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, or doing the e to the x 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That may be all we need. And we don't need just the beautiful series, but this is a technique that allows you to manipulate the binomial coefficient, okay? So you can get a really, really nice formulation for the infinite series. And I think it's kind of neat, and it gives you, for you computer science people, this gives you a very nice formula that can be manipulated in programs and all. So with that said, there's a plus and a minus. If you just need a few terms, generate them term by term. If you need a full-fledged formula for a program or something that more difficult in the sense of maybe if you're solving a differential equation, you may only need a few terms. Or if you can generate a nice power series solution that's infinitely stated, then that's good too. It just really depends on what the problem is asking you to do. Right now, this is just good practice working with series. Now, there's an example here. When it comes to doing and working with these particular types of constructions, I had an example here that I thought was fairly interesting. Let me see if I can find it. It was working with, oh yeah, here we go. When you look at problems like this, you can make substitutions all day long. You don't have to start from scratch. Maybe what's going to happen is that you got this same series, but you're going to replace x with x cubed. Well, that's the only difference right there. You'll get x to the 3n. Everything else will be the same. So once you develop a series, you can reuse it, okay? For simple modifications where you just replace the x with maybe x squared, but then you get x to the 2n there, okay? All this would be the same. So you have the luxury of being able to use some algebra. So that's what I want you to do in your homework, where it says use your cheat sheet to write this series. I want you to do it. I want you to use the polynomial long division or multiplication. I want you to replace the x with something more convenient. Like if you need e to the 2x, just replace x with 2x in your series for e to the x, and you're done. You're a genius. It's like, oh, wow, why can't every math problem be this simple? Well, one thing that's kind of interesting is the following example. Say, for instance, you had this example. And the first illusion was to say, okay, use your cheat sheet. So it would say something like this. I hope you've enjoyed the little excursion with the binomial coefficients. It's fun. Enjoy that. Look at the notes that I have on Blackboard and use what I've done today. I've tried to give you both sides of the argument. So for instance, we could say write a Maclaurin series, for f of x equals the square of cosine. And you're thinking, oh, no, not going to do it. Well, there's no work to be done. We know what this equals, and we can use the series that we already know for cosine. So observe. This is meant for you to use what you've already constructed. Observe that cosine squared x, this is just power reducing. This is your friend. You could say this in your sleep. This is 1 plus cosine 2x. This is what I was talking about before. I had a really brilliant student one time that was tutoring in the tutoring center, but maybe about 6 years ago, 7 years ago. Professor Ron, I'm trying to integrate e to the x squared. This is so hard, I can't do it. I said, well, you're using the series for e to the x. Oh no, sir, I'm starting from scratch. I said, you're a smart person. But again, he didn't take me for calculus 2. So I said, that's all right. That's all right. Let me show you a way to use what you already know. Oh, that's so great. He says, don't tell anybody I didn't figure this out. I said, please, that you're asking is what makes it you a good student. The student right now is working on a PhD in computer science and will probably end up being the next Bill Gates. I will not be surprised. It's amazing some of the students I've taught, but everybody has to start somewhere. You start somewhere and then you rise to greatness. Whatever that greatness may be, it will change the world. So when you look at this, you're thinking, okay, this is 1/2 plus 1/2 cosine 2x. Now 1/2 is fine. That's a nice convergent series, right? It has one term. And of course, cosine 2x is a series we know from our chart. So this is done. So now from the chart, I'll just say chart instead of cheat sheet. We know the Maclaurin series for cosine, so we're going to replace the x with 2x. So this is 1/2 plus 1/2. And I'll just write over here just to remind you. Remember the cosine x n equals 0 to infinity, using the formulation with the summation, we have -1 to the n. We have, in this case, again, even powers. Remember, cosine is an even function, so x to the 2n divided by 2n factorial. Remember the 2n factorial on the outside, just like the 2n plus 1 quantity factorial for the sine. So now we just substitute. So now the cosine 2x will be 1/2 n equals 0 to infinity, -1 to the n. We replace x with 2x, 2x, 2 to the n, 2n factorial. So the thing is, at this point, if you wanted to, you can use your laws of exponents and rewrite it, but you're done. You're done. So that's it. For instance, you could just write the 2 to the 2n to give you 4 to the n, and then x to the 2n if you just wanted to rewrite it a little bit, but it certainly wouldn't be required. So the idea is that we can do replacements. It's like we replace x with powers of x in the algebra of the polynomials of the power series. The key here is that we don't have to start from scratch. And I don't want you to think that every problem that you do in this class requires you to start from the very beginning. So what I would recommend with these problems is start out by again printing out this sheet, or just use your ebook where you have all these power series for elementary functions that we've talked about. And if you have a little extra time, you could actually derive the one for the arcsine using the arcsine formula from the very first week of class, just like we did with arctangent. But the nice thing about this is that the series becomes binomial. And that's why you've got all of these nice squares here like we did. You see the 2n factorial, and this is the same thing we had before that we just worked with the square root function. That's where these coefficients are coming from, using this nice little identity here, okay? So you get a lot of bang for the buck. I mean, you get all of this output once you just develop a few useful series. Again, that geometric series was such a linchpin of setting up all of this. So start with these types of problems where you use what you already know, and then go back to the binomial series and practice using the coefficients. So again, what we want to see from the power series in section 10 is that every convergent power series is its Taylor series. So now that you have this nice composite list of power series, you can use them and manipulate them to create new power series basically for free. Okay, so I hope that this has been enlightening. This is really, really fun material, ladies and gentlemen. I know it's not easy, it's not simple, but the idea is that as you work with these problems, you're thinking, look how much I know. I know so much. I already knew this, Professor Ron. You're probably thinking, well, that was obvious. So as you work through these examples in your homework, focus on the ones where you use the chart, and then start manipulating the binomial coefficients to get some nice infinite series representations of the power series. So like I said, I will have the jury duty on Wednesday. So I'll send out another announcement about that, and I will eventually put up a recording of the lecture for our next topic, which will be parametric equations in chapter 10. So again, I've got my civic duty, so you all will get to rest on Wednesday. Maybe you can sleep late, but I appreciate your affording me that. I certainly want to make sure that I keep the powers that be, so I can continue happy, so I can continue to do what I love to do. So you all have a great day. I appreciate your attendance this morning, and I look forward to seeing you at my office hours. Take care.